Okay, good afternoon, Zoom and on-site participants. Welcome to join Innovating to TechTalk. Today we are happy to have Dr. Ximing Zhang, Assistant Professor from Department of Electrical and Electronic Engineering, to be our moderator. Without further ado, Dr. Zhang, please.
Okay, so thank you, Key, for the introduction. And it's my pleasure today to introduce my colleague, Edith Ngai, for the as the presenter today. And she is currently an associate professor in our Department of Electrical and Electronic Engineering at HKU. And before joining HKU, he was an associate professor in Department of Information Technology in Uppsala University, Sweden. And her research interests include Internet of Things, machine learning, data analytics, and smart cities. She won a Weimar Fellow awarded by Swedish government research funding agency, Vinnova. She's a fellow of Center of Water Technology and Policy at HKU. She served as a program chair in ACM Women Courage 2015 and a TBC co-chair in IEEE Smart City, IEEE ISSNIP, and IEEE GreenCom. She was the area editor of IEEE Internet of Things journal from 2020 to 2022, and also associate editor in ad hoc networks, computer networks, and IEEE transactions of industrial informatics. So a lot of things, and I decided to stop here. I took your time to her, and without further ado, so let's welcome Edith. Yeah.
Thank you, Shimin, for the introduction. Very kind of you for coming today. Yeah, so it's my pleasure to be here today to talk about our latest research on IoT and machine learning for smart water auditing. So this is a joint collaboration, joint project with Hong Kong U Water Center, Faculty of Engineering and Faculty of Social Science. So before I start, so I want to know if you heard about AIoT or IoT. Yeah, probably yes, hopefully, since we are engineering. Yeah, so I think the term IoT has been there for 10 years now. Yeah, Internet of Things. Yeah, so recently, because of the advancement of artificial intelligence, so we come up with like a modification, minor modification on IoT because we want to make it more intelligent. So we have the new term AIoT, that's artificial intelligence of things. Yeah, so basically the idea is similar, but we are trying to combine IoT with sensors and communications, data collection with artificial intelligence. Yeah, so we still have like a lot of sensing devices like on the right-hand side, like smartwatch, embedded devices, different kind of sensors, and now we have smart vehicles. So they are actually the things that we mean here for collecting data from the environment or from human bodies, like if it is a wearable device. Yeah, and then with these things, we can collect a lot of data. And but the data could be large amount and it might not be very easy to interpret. That's why we need some techniques like data analytics, machine learning, artificial intelligence to process those data, to extract some useful information out of those data. And then usually we will combine with cloud services because we have to store the data, process the data, do computation, and maybe provide visualization to users. And then after that, we get some insights, and then the information can be usable, and we can use it for different things. Like for the IoT system itself, then we can do a lot of system optimization. But in terms of application, then we can do resource allocation. We can have business and household decision making. We can also, for social science colleagues, do some public policy design. Yeah, and then this kind of decision making and optimization operations could be realized in different kind of applications, from smart transportation, smart homes, smart cities, smart health, or sustainability, environmental protection, and some other kind of management like supply chain or even more. Yeah, so we want to give feedback to the environment, to the system, or to human beings, so that we can achieve our goal. For example, in smart water auditing, I think that eventually the goal is hopefully to reduce the water consumption. Yeah, even though we know that it is not very straightforward and it could be a long way to go. Yeah, so here on this slide, actually, it just shows you some example applications around us every day. Actually, maybe you didn't pay a lot of attention, but we are actually living in a smart city. Yeah, so it is getting smarter and smarter. So for example, we can see a lot of smart buildings. Maybe you can sometimes you feel, oh, my building is not very new yet, but actually there could be a lot of sensors already inside the system. For example, we have air conditioning system, we have ventilation, we have lighting systems. Those systems have sensors to sense the temperature, the light intensity, occupancy of people, yeah, and air quality. So a lot of things just maybe we don't see or we didn't pay attention before. Yeah, so on vehicles, you know, we have autonomous driving nowadays. So cars are becoming smarter and smarter, and they can understand like the scenes on the roads, and they can make decisions. And in the future, we don't need drivers anymore, and the cars can drive by themselves. And if you read magazines in IEEE, then you know cars can talk to each other, and they can communicate. And cars and also cars with the roadside infrastructure. For example, the traffic light, and maybe we have also sensors on the roadsides to take pictures on the road to find illegal parking, illegal entry of vehicles, and a lot of applications like counting the number of trucks passing by, and some sensors can be under the road and can measure like the weight of the trucks, for example. A lot of applications, and in the park, then we know that actually, some university have investigate sensors to try to measure the tilt of the tree, so that they can identify which trees may fall, have the risk to fall. Then they can fix it before falling. Yeah, so there are many applications, and of course, new applications will come up. Yeah, so that's why you're here today, and that's why you're studying engineering. Yeah, but coming back to the project that I will present today is about smart water auditing. So this is a joint project with Hong Kong U Water Center. So the goal of the project is to collect data and provide insights on how water is being used in households of Hong Kong. Yeah, and I think the eventual goal is that we want to raise the awareness of people, how much water they have been using, and hopefully eventually we come up with some schemes or policies that can encourage people to reduce their water consumption. Yeah, so if smart water auditing is a new term to you, so basically we are using technology to help us to monitor like water consumption, and it can be of course extended to how the water is being delivered or processed. Yeah, if it is from the angle of water supplies department, but from us, yeah. So in the project, the beginning of the scope, we focus more on like measuring the water consumption. So in order to understand how people use the water, actually we want to know not only the total water consumption, we want to know how much water has been used in different categories. For example, in this pie chart, you can see we can show like 27% of the water has been used for showering in this case, and 15% by the washing machine, and some other by kitchen and bathroom. So this is just a random example. Yeah, so in Hong Kong, actually, we seldom use fresh water for flushing the toilet, yeah, but in some countries, that may be more often. Yeah, and then you may think about, oh, is this project well motivated? Are we Hong Kong people using too much water? Yes, so this is some statistics I got from our colleagues in social science. Yeah, so you can see actually Hong Kong has a rising trend on the volume of water consumed. Yeah, while in the opposite, if you look at other big cities like Tokyo, Seattle, New York, they all have like a declining trend. Yeah, so actually, sustainability is actually a common goal in major cities, in all kinds of cities worldwide. So it's always good to preserve our environment and use less resources, use just the resources that we need, but not more than what we need. Yeah, because actually not only water, but it consumes also energy and resources and cost to process and deliver the water. So it's not only the water itself. Yeah, so it's always good to do something good for the environment. Yeah, so coming back to the project, Smart Water Auditing, actually, to make it simple, actually, the logic flow is like this. In the project team, we develop together this smart meter analyzer, which can be used for smart meter automatic meter recording. Yeah, so we want to transmit the meter data automatically to the server so that we don't rely on people just go there maybe every few months to look at the reading, and we can obtain more fine-grained water consumption data. And the time series data can be used for data analytics. And if we fit this data into our machine learning model, if we have trained our machine learning model, actually we can try to disaggregate the water consumption. So we can come up with like a result, how much water has been used for showering, how much for kitchen use, how much for washing machine, etc. And this information could be visualized and easily understandable by the end users. And we hope that it can give them some motivation to know more their water use habits, and hopefully try to come up with some policy that can encourage them to reduce their water consumption. And then it will give like a feedback loop to the environment, and hopefully the environment will be more sustainable, will be better, and we can continue to collect more data, and then it will be like a feedback loop and creating a positive effect. Yeah, so the way to use the system is actually pretty simple. We just need to install our SMAN, Smart Meter Analyzer, on some existing building meter from the water supplies department. So those traditional building meters are mechanical. They don't have this automatic meter reporting functionality. Yeah, so with our SMAN, with this smart meter analyzer, we can obtain the data automatically from the smart meter, and it is more fine-grained data, not just visited by the staff of the water supplies department every few months. Yeah, but could be continuous, every hours, every few minutes. Yeah, that's possible. And then if we fit this time series data into our machine learning algorithms, then we can get output like how much water has been used in different water end use categories. Yeah, so in our project, we focus on showering, bathroom basin, kitchen sink, and laundry. And it could be, of course, extended in the future. So before I go into the details of individual hardware component and the machine learning model, here it shows the overview of our system architecture. Yeah, so our project team built this complete system. You see, we have developed our smart meter analyzer, which could be mounted on a mechanical building meter from water supplies department. And then this box can take picture on the images, the meter readings, and then translate into numbers and transmit those data through NB-IoT network to the cloud server. And then after anonymization, it will be further moved to our machine learning data cluster inside the Hong Kong U network. So we can do a lot of machine learning, model training, and inference. And the inference results like the end use categories and volumes will be transmitted, will be shown on a mobile website so that our participating households can view how much water they have been using in different time intervals, daily, hourly, weekly, or yearly. And thanks for the project team, actually, we have developed this SMAN hardware configuration. You see, we have a two-part in our device. This part is called a SMAN image sensor box. Yeah, so I will show you the interior of this box. So basically, it has an opening for viewing. There's a viewing window on the top. Yes, you know why? Because the water supplies department staff still will come and visit those meters, and they use traditional method, but just look at the reading and note it down and record it, and then report to water supplies department to compute like how much we have to pay for the water bill. Yeah, so they still use this method. Yeah, but for our research, of course, we explore some new technology. In the meantime, we don't want to interfere their service, and they don't want to be interfered as well. Yeah, so that's why we still have this viewing window. And then after getting those digits, those numbers, then the number, of course, will be transmitted to another box here. Actually, this box it stores the battery, and also it has the data log and with the communication for NB-IoT. So we connect these two boxes through power and data cable so that we can transmit the time series data from this billing meter to our server. Yeah, so to go through the steps again. Yeah, so in this smart meter analyzer or SMAN, then we take pictures of the smart meter reading and then feed the image into a machine learning model for optical character recognition. Oh. Oh. Oh, okay, okay. Okay, yeah, so thanks for the reminder from our director in the Hong Kong Water Center. So he suggests that maybe we shouldn't take pictures here, yeah, because there's some IP rights on the pictures that we use here just for the project safety reason. Yeah, so maybe we don't do that. Yeah, so okay, so let me continue with the presentation. Yeah, so we want to digitize the record, and then we can accumulate the record before we send the record to our cloud server, say in a batch. Yeah, through NB-IoT technology is actually new wireless communication technology in cellular network for IoT devices to report data. Yeah, and then we can obtain time series data, which can be reconstructed on the cloud. So this is actually just the total water consumption based on the water meter reading. Yeah, so later on, we still have to process this data, and we have to train our own machine learning model to be able to disaggregate the total water consumption into different end use water consumption. Yeah, so here you can see our water end use disaggregation results. So this gray area just shows the total water consumption. Yeah, so this is coming from the readings of our billing meter. But then later on, we have to run machine learning algorithm so that we can disaggregate the data. So now we know how much water has been used by the washing machine, this green, blue, green color, and how much by the shower head when people are taking a shower, and how much by the kitchen type or the basin type. And you can also see different patterns in terms of water consumption. So the patterns are very important for us to classify those water consumption data. Yeah, so now it comes to an important part. Yeah, so we have this SMAN, which help us to collect fine-grained total water consumption data from the billing meter. Yeah, but how to obtain the output with end-use categories? Then actually we have to train a machine learning model to do that. Yeah, so I think most of you are familiar with machine learning. So in order to train machine learning model, what do we need? Labels, yes, we need labels. We need training data with labels. Very good, thank you. Yeah, so how can we obtain those labels? Is it easy? Actually, it's not very easy. You know why? Yeah, because now we are trying to know the water end use. It means that the labeled data should actually label the amount of water coming from which water type, right? Type. Yeah, water type. Yeah, then, so how can we get those ground truth data? So actually, it's a huge effort for the project team to come up with this data collection scheme. Yeah, so we conduct a pilot study. Actually, we deploy many sensors, based sensors in 21 households. So 21, it doesn't seem like a big number, but actually it's not only on the building meter, it is on each water outlet. So it means that in each household, maybe we have 5, 6, or even more sensors being deployed. Yeah, so you can see the effort of our engineers in the team and researchers. Yeah, so this is a deployment at our shower head in one household, and this is the basin type, and here's the washing machine and the kitchen type. Yeah, so actually it's quite a huge effort to collect ground truth data because we have to deploy a lot of sensors. Yeah, and you can, from this slide, you can observe also different water consumption pattern. For example, for showering, you can see that the duration of each event flow would be longer. Because usually we turn on the shower and we wash, and so we will not be like in the basin type, we spend very little time when the water is on and just quickly wash our hands. So these patterns are different, and they are important features for us or for our models to be able to distinguish whether this time the water flow is on the shower head, on the washing machine, or on the basin types. Okay, while we are doing the deployment, and actually after that, we also want to try to get a feeling like how high sampling rate we need in order to be able to get satisfactory classification accuracy. Yeah, so we run on a well-known SVM model, support vector machine. Yeah, so it's a very classic model. Yeah, and then we try to vary the sampling interval. Yeah, so you see on the x-axis, y-axis, yeah, TS, the sampling interval starts from the top 1 second. So every second we get samples until every 60 seconds, every minute. Yeah, so when we increase the sampling interval, it means the data collected will be less fine-grained. We may lose some information. That's why the classification accuracy will also decrease. Yeah, so if we have high sampling rate, then the accuracy will be higher, and a lower sampling rate, the accuracy will be lower. Yeah, and then you see that, of course, there's a trade-off. Yeah, so if we sample very often, it means that it consumes a lot of energy and also a lot of communication overhead. Yeah, so there's a trade-off. So maybe we shouldn't choose 1 second, and we should not choose 60 seconds, because then the accuracy drops too much. And maybe somewhere in the middle, maybe 5 seconds or something. Yeah. And here you see 2 different bars. Yeah, by volume, it means the percentage of total volume of water that is correctly classified by looking at the volume. Yeah, and by event occurrence means that we count like the number of events, the percentage of events that we can correctly classified. Yeah, so the volume accuracy is higher than the event occurrence. So there are different reasons. So one reason is that maybe it's easier to classify large volume events like laundry or showering. So maybe they have more obvious patterns. So we have higher accuracy. And for those events, they also consume more water. So and for counting the events, so it sometimes maybe it's misclassified, but when we calculate the volume, maybe some events cancel out each other. So maybe that's why the volume can obtain higher classification accuracy. Yeah, so in terms of the deployment, actually, we explore different sites in Hong Kong, because when we look for those participants, they are actually spreading around at different locations. And in total, we have deployed more than 100 sensors. If I remember correctly, maybe 123 or something. Yeah, but maybe that's not very important. Yeah, so, and Hong Kong is a very special city. It's very dense with a lot of high rise. So I know many foreigners coming to Hong Kong will be very surprised. They have never seen this before, probably. Yeah, so it could also be actually a challenge for cellular network, whether we can run on this NB-IoT for data transmission. Yeah, because there's so many buildings, so how will the signal propagate? And we have a medium density location, a high density location, and very high density locations. So as a side study, we actually also look at like how this NB-IoT technology is running in Hong Kong, whether the performance is good or not. Yeah, so NB-IoT is pretty new. Yeah, so it's originally supported from 4G, and of course 5G will provide NB-IoT technology, and it's designed for a low cost and low power and lower data rate transmission, especially for these small devices, IoT devices. Yeah, so our timeline is around here. Actually, we are among the first testing IoT technology in Hong Kong in a larger scale deployment. And we come up with also some interesting measurements, if you may want to know. Yeah, so we measure this RSRP. Yeah, it is related to the signal strength received by the end device, like the sensors from the cell tower. Yeah, and we found that, when the RSRP is higher than actually the signal strength is stronger. Yeah, so and something interesting here is when you see the density is very high, why we will get actually higher or better RSRP. So actually, we have been discussing this among the team, and we think that maybe the cell towers will be deployed with higher density if we have more users in dense areas. So maybe this is why the distance from the end device to the cell tower will be closer, and it leads to stronger signals. Yeah. Yeah, but on the other hand, we found that if the device is deployed, like the sensors is deployed in deep indoor environments, say it's not very close to the door, and it could be covered by some cupboards or walls, then actually the signal strength will decrease. Yeah, another metric that people commonly use to measure the cellular signal is RSRQ. Yeah, this is more related to the signal quality because it also accounts for the noise and interference. Then in this case, then we can see that actually in medium density, then the RSRQ will the quality of the signal will be better. Yeah, so I guess it is because in highly dense environment may be more interference. Yeah, and then the signal may suffer and have an attenuation. Yeah, so yeah, so this is just like some side measurements that I think it is interesting because we are among the first to do large scale deployment and measurements with NB-IoT in Hong Kong. Yeah, but going back to the important part, that's the machine learning part. Yeah, then actually we also do some advancement in terms of the machine learning model. Yeah, so different from traditional event-based classification method. Yeah, because when we look into the literature, we find that existing methods on water end use classification are mostly event-based. So it means that they will basically look into the water consumption and then identify individual flow events. So a flow event is defined as an event. The time starts when we turn on the water tap, and then it ends when we turn the water tap off. Yeah, so this is one flow event. So in this figure, there are already 4 individual flow events. Yeah, so in traditional approach is event-based. So we just want to classify the type of each event. Yeah, and only one event input and then we expect only one output for each event, only one category per event. Yeah, so it also implies that we have to do disaggregation, some pre-processing before we can fit the water consumption into the machine learning model in traditional event-based categorization method. Yeah, so and traditional categorization method include like the one that I showed you before, SVM or ANN. Yeah, but of course, it suffers from some limitations. And in the project, we also try to explore how we can improve those traditional methods. Yeah, then actually my MPhil student comes up with this solution. Yeah, thanks, Peter. Yeah, so and we realized that actually in the traditional methods, we are not able to capture those inter-event patterns, which could be quite important in water end use classification. Because if you look at, for example, the laundry cycle in the washing machine, then it will be very easy to identify they are quite similar and related in terms of duration, volume, and the inter-event distance, right? Yeah, so if we can capture this kind of inter-event patterns, then we believe that it can greatly improve our classification or disaggregation accuracy. Yeah, so this is why we want to come up with a machine learning model that that is not just event-based, but it can also capture inter-event patterns. And another thing is about a time of the day information. By observing the data, we find that actually human beings have habits. Yeah, so we do cooking during around lunch hour and dinner time. So maybe this kind of time of the day information could also be very useful when we perform water end use categorization. Yeah, so and we want to have the model that can capture this kind of information. Yeah, and then it come up with our proposed method. So we call it an accumulated use categorization method. And actually it is a UNet-based model. Yeah, so the good thing of this model is that we don't need to perform pre-processing to disaggregate the data before we can perform event or water end use classification. But we can just fit in the whole time series water consumption data, and then it can do both the disaggregation and classification at the same time. Yeah, and UNet is able to capture inter-event patterns, and it can also consider the time of the day information. Yeah, so maybe just give a little bit more background on UNet. Yeah, so actually it was originally designed for medical image segmentation. Yeah, so we want to, for example, look at the image to know where is the tumor. Is this a tumor or that? And it is useful for the doctor to decide how to cut like the tumor in the operation. Yeah, and later on, I think it was proposed in 2015. Yeah, and then after that, this UNet has also been explored or used in different domains. For example, for audio source separation, say if we can input a audio file with different audio streams, then it's possible to separate the sound, for example, from the guitar, from drums, electronic piano, or from the human voice, the singing, yeah. And similarly, some people explore non-intrusive load monitoring, say whether we can disaggregate the power consumption data, yeah, like in a household, or yeah, then how much electricity has been used by a different kind of electrical appliances. Yeah, but we are the first to use it for water end use categorization. Yeah, and of course, in order to make UNet performing well in our program, we have to do some adaptation, and then we make some changes in the original UNet design. For example, we use ResNet backbone, and we use depth-wise convolution to reduce floating point operations and make it more efficient. And then we extend the CNN kernel from 3 to 9 so that we can consider more time steps when extracting features. And we also changed the activation function from value to GALU so that it could be smoother and I can capture more information. Yeah, and in terms of the optimization function, then we actually use dice loss. So dice loss actually is a common index for measuring how good the segmentation results is. It comes from image segmentation originally. Yeah. So if we look at the top right corner, it explains like the dice coefficient. Yeah. So it explains. It tries to capture like how good this blue and red is being the common area actually is trying to see. Say if the predicted results and the ground truth overlap each other, then it is a very good scenario. Then the dice coefficient will be 1. Yeah. Yeah, and then dice loss is just 1 minus the dice coefficient. Yeah, so we want to minimize the loss when we train our machine learning model so that we can obtain accurate classification results. Yeah, and the good thing to use Ngai laws is that it can weight all classes equally so that it would not have bias towards some dominating class. And here is some example results. On the top is the ground truth, yeah, and at the bottom is the prediction. So you can see that actually the prediction results looks pretty similar to the ground truth, but of course not exactly the same. So we successfully identified the laundry, several event flows. Yeah, but for the first one, actually some of the kitchen use has been misclassified as laundry. Yeah, so of course no perfect model, so mistakes common. Yeah, but overall the performance is satisfactory. Yeah, and we try to do more analysis and then we compare our UNet model with some traditional models like the SVM model and the ANN model. And you see we divide into two parts here, the perfect disaggregation and without disaggregation. Yeah, so because it is, as you know, SVM and ANN require preprocessing for disaggregation, but actually it's very difficult to obtain perfect disaggregation. That's why the accuracy might not be very high if the disaggregation is not perfect. Yeah, even though if we assume perfect disaggregation and then we just look into the classification results, we see that UNet can still obtain higher accuracy compared with the existing models. Yeah, so now it comes to the conclusion. So basically, my talk introduced and described the IoT system that we developed to collect water use data from tap-based sensors and our smart meter analyzer. And we train our machine learning model based on UNet, and so that it can perform household water and use disaggregation. So we, through our experiments, we show that our model is able to provide higher accuracy compared with existing event-based methods. Yeah, so actually the team is working hard and continuing some future works. Yes, a lot of future works to be done. For example, just some examples here, how to extend the battery lifetime of SMAN. Yeah, and we are also continuing with a larger scale deployment, and we are exploring new application sites. So other than households, there may be schools or commercial buildings in the future. And we are also looking into new kind of sensors to do this auto meter reading reporting. And so I really want to acknowledge Hong Kong U Water Center. It's a really meaningful and fruitful collaboration. I really enjoy a collaboration with our colleagues in the center and from the Faculty of Social Science. Yeah, I think it's a very nice collaboration between the two faculties. And I personally have learned a lot through the collaboration, not only on the engineering side, but also like the policy side, the social science and the environmental side. And I think it's really meaningful to the society. Yeah. So thank you. So that's all for my presentation.